Okay. Hi, everybody. We're back. Here's an idea of data coming in. So let's say you're out on a trip with your dad and you stop finally at your favorite McDonald's on this road trip that you're on. And of course, it has to be open. We don't know if McDonald's is open right now, but we'll pretend it is. And then you get back in the car and you start talking to him, and he is so tired of listening to you talk, and he says, "Can you just work on your calculus, please?" And you're sitting in the back seat, and what he doesn't know is that you have your phone with you, and you open up Waze, and every minute or so, you look at his speed. So the first time, at time t0, that you look at his speed, it's 50. Now, your dad's probably trying to go 70 because he's on the expressway, but we're going to pretend like he's only doing 50 because that's an easier number for me to deal with. Next time you look, delta t later, he's still going 50. But at the same time interval later, he stopped because there was construction on the freeway. And this is when your dad is saying all these nasty things and he doesn't really want to talk to you. That's okay. Now, we can start plotting that. This is what you would have done if you wanted to plot the speed against time, 50, 50, 0. And you might even think, okay, I can connect those with my velocity line. He has this cruise control here, but then he had to stop. Now, it's not going to be like complete breakdown like this because you didn't get in an accident. So you know that the curve has to come down something as a quick stop. And then you were stopped for a little bit, and then you started to go slowly for a while. And finally, with all of these numbers, you can kind of fill in the graph. What you would have used that graph for months ago is you would have said, I don't know where we are on this trip, but if I look at the area underneath the curve, I'll have the total distance that we have gone since we stopped at McDonald's, or an approximation. And in fact, since you don't have an explicit curve, you would even just make little rectangles or trapezoids or something to find that area underneath the curve. All right, so now what we're going to do now instead, that was the old way of doing it. Now we're going to look at the new way of doing it. And what we're going to try to do instead is, instead of graphing the velocity function from our data, we're going to actually try to graph the distance function. We'll call it d. And so at time t0, we know that the slope of the tangent line to the curve, because that's what a derivative is, that's what the speed would be at this point, is 50 miles per hour. And so instead of putting a dot like we did up here, we're going to put a little tangent line with a slope of 50. Now, that only looks like a slope of 1 if you think about it, but I'm going to make the units so that, because that'll make it easier for me to draw. So there's my little tangent line slope. Think about the example that we used before. I don't know a particular solution to this graph yet, so I don't know if the tangent line should be drawn here or here or here or here. I don't know where this tangent line should be drawn, but there it is. Then I go to the next point, my T1, and say, oh, he's still doing 50. My tangent line then still has slope 50, so I put some more in there. And again, I don't know where these are. At time T2, though, that's when he stopped. So my tangent line, look back up here, my tangent line has slope 0. So I put little tangent lines with slope 0. What I'm doing is building what is called a slope field by looking at little pieces of derivative. When he starts up again at T3, he's not going quite so fast yet, so our slopes are a little less than the 50 miles an hour. When he gets up to speed again, they're going to be 50 miles an hour again. And they're going to stay at 50 the next time. And then we finally get towards our destination, so he starts to slow down again to 35. And finally, we're there, and we stop. And if you kind of squint your eyes, let me get my black pen out again. If you squint your eyes, you can almost see what the graph of the distance function would look like. It kind of does this, and then it comes up like that, and slows up, and then we're there. And if this were the particular solution we'd be looking for, we could actually just come over to our y-axis and figure out how high it is, and that's how far we've gone. That would be the area underneath the curve. Pretty cool, huh? Let's look at what your book says to do. Let me bring this over. Yeah. Okay, so in example 1, they say, here's a derivative for you. Let's make a little chart up for different times and find out the values for the derivatives, and then plot little tangent lines at those points. And that's what they've done. And then they jump and they say, by the way, if we had something that could do smaller increments of time and smaller and little cute little lines, and they were much better, we could squint and follow one of these along the tangent lines and get a solution. Now let's look at the next page, because they actually do that for us. You see? They start at one point and they follow the little tangent lines to find one of the particular solutions. Pretty cool, huh? Okay, let's stop that one now, and we'll do one more.